7.1 is a review of exponential functions. For our warm-up, we're going to change each of these to have the same base, because if a to the x is equal to a to the y, then x equals y. 1 over 3 can be rewritten as 3 to the negative 1. 9 can be rewritten as 3 squared. Simplify. So now exponent equals exponent. And we get x equals negative 1/2. An exponential function is a function represented by a constant base with a variable exponent. For example, 2 to the x, e to the x, 3 to the x squared minus 5 are exponential functions. For a and b, positive real numbers, and x and y, any real numbers, these are our properties of exponents. When simplifying, do not leave answers with negative exponents, and go ahead and simplify these without using a calculator. 27 to the 1/3 is just cube root 27, so 3 is now to the power of 4. That's 81. Anything to the power of 0 is 1. I'm going to reduce the inside first. Simplify the numerator. 1 over e to the 4. The base needs to be the same for you to be able to add the exponents or subtract the exponents. Here our bases are not the same, so I'm going to rewrite 25 as 5 squared. Now it's 5 to the 3 times 5 to the negative 4. Now that I have the same base, I can add the exponents. Same as with the warm-up, we're going to rewrite with the same base. 9 is 3 squared. 27 is 3 cubed. Now we have the same base, so 2x is equal to 3, and x would be 3/2. Use a calculator to carefully graph 2 to the x, 5 to the x, e to the x in the same coordinate plane. Do you see any similarities in the graphs? I'm going to plug in negative 1, 0, and 1 into each of these. Each of these exponential functions has the same y-intercept. They have the same horizontal asymptote of y equals 0. And all three of these functions are increasing from negative infinity to infinity. As a review, the graphs of exponential functions, we have a domain from negative infinity to infinity, but the range is based on the horizontal asymptote to infinity. The horizontal asymptote will be 0 when your form is a to the x, not when there's a vertical shift. The graph of f of x is continuous, increasing, concave upward, and 1 to 1, meaning it has an inverse function. And the y-intercept is always 0, 1, again, unless there's a shift of some type. The letter E used as a base in examples 2, 3, and 6 is not an unknown. We know this number. It's the natural number. It is a number called the natural base for exponential functions. It is the most common base in calculus because functions with base E are easier to differentiate and integrate than functions with other bases. By definition, E is the limit as x approaches 0 of 1 to the x quantity to the 1 over x. And to 3 decimal places, that would be 2.718. Without using a calculator, sketch the graph of e to the x. E to the x was already in our previous example. And now using adjustments to the graph for example 7, graph f of x equals e to the negative x plus 1 without using a calculator. Write an equation for the graph's asymptote. E to the negative x means a reflection in the y-axis. Adding 1 to the end of the function means a vertical shift up 1. E to the negative x without the shift would look like this. Now we take this violet graph and shift it up 1. Before the vertical shift, the horizontal asymptote was y equals 0. But after we have shifted up 1, the horizontal asymptote of this new graph, f of x, will be y equals 1.